We now look at complex numbers and the sort of questions that they can ask, not about complex numbers, but about how they might use complex numbers and another part of your course together in a sort of a, project maths type question, where they join two bits together. We've done all the complex numbers, but we're just joining the two together. Here we've got complex numbers in terms of arithmetic, and we have exactly the same BIMDAS, or please excuse my dear Aunt Sally, order of operations when it comes to dealing with additions and subtractions. We must do brackets or parentheses first, indices, multiplication, division, addition and subtraction. So here we've got a question where we're asked to simplify the expression 3 plus I into all of this. And we do it as if it was just pure numbers. We say we have I into this, but we also always do brackets first. So we write it down and we say, but within the brackets we have an I squared. The I squared is parentheses, so we're going to change that I squared to a minus 1. Other than that, everything is the same. Inside, we still work on it because we've got multiplication in there, so 3 by 2i gives us 6i. Now we can start joining things together. The 6i and the I can become 7i minus 1, and that's about where we stop. Now we've got to look outside. The I is really times or multiplication, so we might multiply in 7i squared, because I by I is I squared, and minus I. We're now stuck again with the I squared, it's the power, so that's going to become minus 7. 3 minus 7 minus I, we can do the subtraction. But remember we to do it in pairs, the reals and the imaginary separate. Minus 4 minus I, and that's it. So that's one type of question that can come up. There's also something very subtle going on too in complex numbers. Here's a point, and they say u is a plus bi, v is c plus di. If two numbers are equal, if two complex numbers are the same, if u and v are equal, then the real parts must be equal and so must the imaginary parts. If somebody says I'm on the position 3, if I'm out here in the complex world and I've come to this particular point here and it's 1, 2, 3, 4, 5, 6, and it's 1, 2, 3, 4, 5, 6 plus 5i. There is no other way of getting there other than taking 6 and 5. You can go 5 and 6, 5 imaginary and 6. But if somebody said that is the number a plus bi, and it's also c plus di, there aren't any other possible combinations. A must equal 6, or C must equal 6, and D must equal 5. Now, that's a bit theoretical when they say it like that, but I'll show you how it applies in a question. They're saying if two numbers are equal, then their real parts must be equal and their imaginary parts must be equal. So here's a question where they say s plus ti is 1 plus 3i squared. Now, some of this is sort of like before, where some of it just involves multiplication. So 1 plus 3i squared is really just shorthand for 1 plus 3i by 1 plus 3i. And that's straightforward multiplication. First outside, inside, last. So we'll do all that, 1 plus 3i plus 3i plus 9i squared. That turns out to be minus 8 plus 6i. So we do it 1 by 1 is 1, plus 3i plus 3i plus 9i squared. The 9i squared becomes the minus 9, etc. That's the right-hand side. But on the left-hand side, we had s plus ti. So s plus ti is minus 8 plus 6i. But if these are equal, then s plus ti must equal minus 8 plus 6i. And if we call this the real and the real, the imaginary and the imaginary, the first real must equal the second real, and the first imaginary must equal the second imaginary. So s must equal minus 8. And ti must equal 6i, t must equal 6. So hidden in that, they found a way. It looked off-putting, because you'd look at that and you'd say, not only is it complex numbers, but there's two variables as well. But if you work it out, it's actually quite straightforward. Here's another equation now with one variable, where they say, solve the equation k, w plus w bar is 20, where w is equal to 2 plus 5i. This is where it's important to know your symbols and your nomenclature there. That symbol w bar means the complex conjugate. It's the one that goes with the mirror image. It's 2 minus 5i. So now we've got 2 plus 5i and the other one 2 minus 5i. Add the two together and we know we're going to get a real number. So 2 plus 5i plus 2 minus 5i turns out to be 4. Not surprising, it shouldn't have any imaginary parts. 4k is 20, k is 5. So it looked off-putting, but it was actually quite straightforward. We now look at two variables. So this is an equation where they say x into 1 plus 3i plus y into 2 minus I plus 2 plus 3i is 7 plus 4i. Lot going on. We look at the reals and the imaginaries and we group them together. And we find that x here is a real. Then you've got a y real, 2 or whatever. So if we work them out, just taking the real parts, x times 1, y times 2, plus 2 is 7. X plus 2y is 7 minus 2. X plus 2y is 5. On the other side, we're going to look at the imaginaries. 3xi here, minus yi, 3i, and 4i. So 3xi minus yi plus 3i is 4i. Just dividing everything by I here, 3x minus y plus 3 is 4. 3x minus y is 1. These are two simultaneous equations. 3x plus, x plus 2, well, I'll write them out here. X plus 2y and 3x minus y is 1. Nothing to do with complex numbers. You can now solve those in your standard algebraic form as you would do another part of your program. But that's how they were spotted in that.